Hello, welcome back. So this is notes 2F, but a little bit of E. So I've learned over the years of teaching this that if I try to squeeze the conversation about the two different types of molecular bonds into the discussion about molecular bonds in general, about covalent bonds in general, that there's not enough time. And so I've learned over the years to put this information on a separate thing. So I've now made it part of notes 2F, but it's technically the end of notes 2E. So that's why it says notes 2EF. When you clicked on the link in Schoology, it should have forced you to make the copy. You should be looking at the same thing I'm looking at. So we're going to continue where we had just finished talking about the fact that molecular compounds have insanely different properties than ionic compounds. And in fact, they even have insanely different properties from each other. And so I want to talk about why that is. How can you have two different compounds that are both molecular compounds, but they don't have the same exact properties, just like ionic bonds? They all have a 3D crystal shape, high melting point, and conduct electricity in water. So I can't give you a lovely list like that for molecular compounds, and I want to show you why. Some atoms pull more strongly on the shared electrons than others. As a result, the electrons move closer to one atom than the other, causing the atoms to have slight, and I mean slight, electrical charges. These charges are nowhere near as strong as in ions and in ionic bonds, but it is enough to make one atom slightly positive and the other atom slightly negative. Pause, get that written down. So now we have a lovely little chart where we're going to look at the differences. So we have polar versus nonpolar. Let's start with nonpolar. So in the nonpolar covalent bond, in nonpolar molecular compounds, the atoms pull equally. I was going to put evenly, but equally is the word I use in the quiz, so that's the word I should use now. Atoms pull equally on the shared electrons. So neither atom is charged. So that is a nonpolar bond. So this is the case when the atoms are identical, like H2, O2, F2, Cl2. So fluoride, chloride, oxygen, nitrogen gas, N2. All of those are ones where it's pulling evenly. So F2 is what I used for the example earlier, so let's keep using that one. So fluorine is in family 17, so it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. And then we have another atom of fluorine, and here we're going to try to be careful to make sure that we put them so that they're the same distance away from the shared pair, because that's the whole point, that neither one of them is any closer to the shared pair than the other one. It's the same thing that happens with our nitrogen. So we had nitrogen with a triple bond, sharing 1, 2, 3, and then the other nitrogen, keeping 2, and then sharing 1, 2, 3. Neither one of those nitrogens is any closer to those shared electrons than the other. So it is a non-polar bond. So non-polar things. Oil is non-polar. F2, as you can see, fluorine, nitrogen gas, oxygen are all non-polar. Carbon dioxide is nonpolar because the oxygens are pulling evenly on the carbon that's in the middle in between them. So all of those are nonpolar. So in nonpolar molecules, such as carbon dioxide, there is no attraction between the individual molecules. All right, so let's talk polar. So a polar bond is a covalent bond where the electrons are shared unequally. Now, this is mean, if you ask me. Non-polar is the one that's equal. And polar is the one that's unequal. Yes, it's mean to do, but at least it's a way to remember it. The one that has the prefix has no prefix in the answer. The one that has no prefix in the answer has the prefix. Sorry. Anyway, so when they pull unequally, it is polar. So this is the case. Most of the time, if hydrogen's involved, it's going to be a polar. If it's hydrogen's involved and it's a covalent bond, it's most likely going to be polar because hydrogen only has one proton in the nucleus. So it's not pulling very hard on that shared electron. Almost always, whatever it is that hydrogen is sharing the electrons with is going to pull harder. Water. H2O, right? And oxygen has 6 valence electrons. And then hydrogen has 1 and 1. Now, here I'm trying to show that the shared pair is being pulled closer to the oxygen. So the oxygen now has more negatives than positives. So it has a negative charge. And then these hydrogen ends have a positive charge. Water is very often called the Mickey Mouse molecule because of this. Oh, that looks terrible. Water is called the Mickey Mouse molecule because of this. It ends up with the two. Well, I think it looks like Kermit the Frog, but Mickey Mouse is what they end up calling it. But I think it looks like Kermit the Frog because we've got the mouth here is the negative of the oxygen, and then the eyes for the 2 positive hydrogens. So examples, of course, would be water. Like we said earlier, hydrogen fluoride, methane, because that carbon is pulling really hard on the shared electrons and the hydrogens aren't pulling very hard. I've got to move myself here. In polar molecules like water, the attraction of the charged molecules makes the water have properties such that it attaches. What's the word I want? Sticks. It's sticky. Sticks to itself and other things. Write these 2 words down. You're supposed to know them already, but just in case you don't. Adhesion and cohesion. Water sticks to itself. Water sticks to other things. That's why water droplets stick to your windshield. That's why water is able to travel up the that's why water is able to why is it doing that? That's why water is able to travel up the straw. That's why it's able to travel up the tubes, the xylem and phloem in the plants, because it's sticky. And so as the plant uses up the water and it evaporates out from the one end, it pulls up another molecule from the bottom. Pause that. Get all that written down. Cohesion, adhesion, water. Go back and pause if you need to while you can see it. Okay. Differences are why molecular compounds can have such amazingly different properties, even though they're the same type of chemical bond, because you can have polar and you can have nonpolar, but they're both molecular. So water, which is a polar molecule, doesn't mix well with oil, which is a nonpolar molecule. So normally by now we would have already done a lab where I gave you some oil in a baby food jar, and then I gave you some water and gave you some food coloring to put in it, color of your choice. I'm going to go with blue. And have you pour the water in and watch what happens. You can see that the oil's here on the bottom. Make a prediction. What's going to happen when I pour this in? Is it going to mix all together? Is the water going to sit on top of the oil, or is the oil going to sit on top of the water? So even though I poured the water in second, it went to the bottom and the oil came to the top because density. The water is more dense than the oil, and then they don't want to be near each other because one's polar, one's nonpolar. So they're pushing each other away from each other. Kind of like the opposite ends of magnets. They don't want to be involved with each other. And so that's why oil and water don't mix. So between density and the fact that one's polar and one's nonpolar, they don't want to mix. Even if I put a lid on this and shook it up, it would still separate back out. Now, I don't have time to really shake it up and really give it the time to settle out. But if you would like to try this at home, feel free. But you can see that the layers are separating out, and that layer of oil is at the top, and eventually it'll all separate out. All right, well, what about when we put in dish soap? So I have some Ultra Deluxe, a totally awesome liquid dish detergent. And I'm gonna put a lot of oil in there, so I'm gonna put a good squeeze of it in and put the top back on. And this time when we shake, yes, it is separated, but only with the foam at the top. All of the rest of the liquid is pretty well evenly spread out. We have and I mean, we're going to start getting some layers. And if we let it sit long enough, we might end up with a separate oil and water layer. But that means that, did I carefully measure out the soap? No. So that means that my chemistry was off. And that's why it didn't work out. So that's why it's so important. I'm just using soap and oil and water, non-volatile chemicals, things that aren't going to create an explosion if I'm not careful about my measurements. But would you want to just willy-nilly if you had volatile chemicals? No. So this is why balancing chemical equations is so important, because if you end up not doing the math right, it might not work out the way you want it to. Now, this pretty much is working out the way I want it to. If I let this sit long enough, it'll do. But so that's how soap works. Soap has, excuse me, soap has a long, complicated molecule that is polar at one end and nonpolar at the other end. The polar end bonds with the water. The nonpolar end bonds with the oil, and it brings it all together. And then if you're taking a shower, if you're washing your clothes, washing your dishes, what do? You then rinse it away. Now think about it. If I have soap and my hands are dry and I use no water, what happens? Right, exactly. You either get this like slimy coating on you or nothing. So you got to have water for the soap to work. You got to have both. So you have the water. You get, if you read the directions on the shampoo, it says to wet your hair first, right? You get your hair wet first. And then you put the soap on. The polar end bonds with the water. The non-polar end bonds with the oil and the dirt, and it brings it together into one molecule, which can then be rinsed away down the drain. And that's how you end up with clean clothes or clean hair or whatever. So here I want you to describe what happened when we added dish soap. And you're going to use your own words, just something about how when we added the dish soap, what happened. So we started with oil on top. I want you to finish. What happened? We started with oil on top, added the dish soap. What happened? Do that in your own words. And then I've also already explained the why. So let's fill in the notes. Detergents have long molecules. One end is non-polar and one end is polar. The polar end dissolves into the water. The non-polar end mixes easily with the oil. All right, now I want you to take a few minutes. Actually, this dotted line should be up here, so it will be by the time y'all do this. I want y'all to pause and use the word bank down here to fill in the quick review, and then I will give you the answers in just a minute. All right, so hopefully you have taken the time to answer these, and now we're going to fill it in. So covalent bonds are formed when atoms share electrons. This type of bond occurs between two non-metals, and it could be more. This type of bond is much easier to break than an ionic bond. molecular compounds are formed from covalent bonds. Some examples are water and oil. Water, however, is a polar molecule, and oil is nonpolar, which explains why they have such different properties, even though they both form through covalent bonds. All right, make sure you've got that. Pause it, check it. I'm going to move on. All right, so you already know the difference between a chemical change and a physical change. So a physical change is one where the material changes form or shape, but it doesn't change into something new. So if you had your homework and I crumbled it up, wouldn't be very nice, but it's still your homework. We could flatten it out. What if I cut it up? It's still your homework. Again, not very nice, but we could tape it together. What if I tore it up? Again, not very nice. We're getting meaner and meaner, but a little harder to put back together, but it's still your homework. It's still paper. We could still find a way to piece it back together. What if I burned it? Right, exactly. It ain't your homework anymore. We now have ash. We have ashes where we used to have homework. So it's not homework anymore. It is a chemical change, one where we created a new material and the old material is not there anymore. So when you want to try to figure out whether or not a chemical reaction has occurred, you can use your senses. And if you use your senses, it can help you figure out that, okay, this is definitely a chemical change because something's going on here. So let's think about toasting a marshmallow. So if we're toasting a marshmallow, what things do we observe using our senses that let us know that this is a chemical change? So for example, first thing I would do is ask, what are the senses? So, tell me, what are the senses? Yeah. Right. Good. Excellent. Okay. So let's start with sight. So seeing, what would we see that would let us know that the marshmallow had been toasted? So a untoasted marshmallow looks different than a toasted one. It would be brown or maybe even black if you're the type that likes them that way. It might be puffier. It might be just bigger. Like sometimes they grow, they expand, right? And they get that crusty outer layer. All right. So all of those things are going to be something that lets you know, we have a different substance, at least on the outside of this marshmallow. All right, what about hearing? What things would we hear that let us know that a chemical change was taking place? So just think about, like, if I'm at a fire, what are the things that you can hear? Yeah, right. You can hear like the crackling of the fire. And you might even hear popping, like a crackling and popping. And then sometimes the marshmallow itself, if you put it up to your ear, it has sort of a crinkle, 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 crinkle sort of sound from the carbon. Yep. All right, what about, we've got sight, we've got sound, touch. What is the difference in touch between a toasted and an untoasted marshmallow? So yeah, an untoasted one is kind of firm, where a toasted one is soft and squishy. Sometimes it might even ooze, right? All that stuff comes out. All right, we got sight, we got hearing, we got touch. What are we missing? Let's save taste for last. So what else are we missing? The one that matters the most when you're getting ready to eat. There's a reason why your nose is on top of your mouth, right? So you can smell whether or not something is edible. So smell. All right, so I don't know about you, but I can smell sugar, and you can smell burning sugar. So to me, it smells like burnt sugar. Like it definitely has a different smell. Now, do untoasted marshmallows have a smell? Yes. I mean, hello, walk down the marshmallow aisle at Walmart. You know where you are. But toasted ones do have a different smell. It's that burnt sugar smell. What about taste? That right? Does an untoasted marshmallow taste the same as a toasted one? I mean, it obviously tastes different. So untoasted, we're going to abbreviate marshmallow as MM, tastes different than toasted. And think about it this way. If I told you to close your mouth and I put a toasted marshmallow and then an untoasted marshmallow, wouldn't you know which one was which? Yeah. All right, pause it if you need to get that written down. So how do we detect that a chemical reaction has taken place? We observe changes in the properties of the materials that result as new substances form. So a gas might be produced. And if that reaction takes place within a liquid, bubbles are going to be released. So when you mix vinegar and baking soda, right? Carbon dioxide gas is being created. How do I know? All those mountains of bubbles coming up. When you mix the stuff that's in a bath bomb, how do I know that gas is being created? Exactly, bubbles pop up. All right, you may also have a color change as a sign that a new substance has been formed. So in the fall, the leaves turn from green to whatever the natural color of the leaf is. I know, isn't that crazy? The color that we see in the fall is actually what that leaf really wants to be. So if it's maroon, if it's purple, if it's orange, if it's red, that's the color, that's the natural color of that leaf. But most of the time when the tree is active, you can't see that color. It's masked by the chlorophyll that's inside of the chloroplasts that are inside of the leaves that are making photosynthesis happen. Well, once the tree goes dormant and photosynthesis isn't happening for a short little while, the leaves are actually already dead. But for a short little while, as the green is leaching out of them, you can see their natural colors. And that is a chemical change. Those leaves are dead. They are going to fall off and new ones are going to be grown in the spring. So we don't get that. It's not like it comes back. So it's another chemical change that we don't get back. The change happens and it stays the same. So a solid might appear when two substances are mixed. So it's called a precipitate. I don't know if we're going to get to do this. Hopefully we will closer to the end of the year. The lab that I normally do with this, we hollow out pennies. So we take old pennies, new pennies. They've got to be from 1985 or newer. And you scratch off one side of them and put them into hydrochloric acid. And there's a chemical reaction that takes place that actually eats away the zinc from the inside of the penny and doesn't touch the copper. And when we're all done, there's this black zinc oxide crystals that are inside the solution that's left. And that's a precipitate. That's the solid that is formed when that reaction takes place. And then cracking or crumbling. So statues, way old statues, very often don't have fingers, toes, noses, chins. If they had curls, sometimes they get broken off. If they had a beard, it gets broken off. A lot of times the surface of the skin looks like it's just full of holes. It didn't always look that way. Okay, so it started out as marble. But then over the years, once the industrial age happened and acid rain started falling, a chemical reaction occurred on the surface of those statues. And it turned from marble, which is a very solid rock, into limestone, which is a soft, crumbly rock. And the acid in the rain made the chemical reaction take place, and you can't get it back. There's no replacing it. What they had to do once they figured out this was happening was move the statues inside, but by then it was too late. And there's no way you can replace a statue that was carved in 600 BC or whatever. Oh, we don't use that anymore. Common Era, 600 Common Era. We're just not going to replace that. So it's one of those things we learned. A chemical reaction is one that produces new materials with properties that are different from the properties of the starting materials. All right, so I want for you to, and again, that's supposed to be all on the same page. So pause, get that. I'm going to fix this. Okay, so now when you see it, it should be a new page for this. So I want you to circle it if it's a chemical change. I want you to cross it out if it's a physical change. So read it, decide, did it make a new substance that's going to have new properties, or is it the same substance, just it changed shape or size or something? So pause the video, figure out all 6 of them, and for you can just put an X type next to it and put an O type next to it. That's fine. And that's not correct necessarily. Oh, is it? Yeah, it is. Oh, well, I gave you the first 2. All right, here we go. Paused it, right? You have all your answers? So chopping an onion, it's still an onion. So it is a physical change. Burning toast, that outer layer is chemically changed into something new. It's a different substance, and you can't get those particles back. Baking cupcakes, again, I can't get the egg and the flour and everything back. I've made it into something new. Water boiling, water freezing, anything boiling, anything freezing is a physical change. A change of state, a change of phase is a physical change. So phase is physical. If you need to write that down to help you remember that. A phase change is a physical change. Leaves changing color, that's a color change, so that is chemical. And a rock wearing away over time in a river would be a physical change. All right, get that written down. Here we go. A change in energy is also, oh, come on. A change in energy is also a sign that a chemical reaction has taken place. When propane is ignited, it produces heat. This is an example of energy being made by a chemical reaction. So when I light my lighter, when I light the grill and ignite that propane, that is a chemical change that is taking place. Some reactions absorb energy while others release energy. One common indication that energy has been absorbed or released is a change in temperature. So we know already that heat, temperature, is a direct measure of energy. The faster the particles are moving, the more energy it has. So there's some types of reactions that need energy, and so they will actually pull energy in. And then there's other reactions that put energy out and release it. So let's talk about those. Pause it and get your answers. Okay, so an endothermic reaction is one that absorbs energy. It makes the substance feel cold as it is pulling heat from the environment around it. So there is no such thing as cold. There is heat and there's the absence of heat. So when something feels cold, it feels cold because it is removing heat from you. That's why it feels cold. So instant cold packs, the kind that you don't keep them in the freezer, but you break it and there's like a bag inside. Now, normally I would have one, but I can't show you this. It would look the same to you. So I didn't figure I would waste that. But ask your parents if you can go buy an instant cold pack. That they have ammonium chloride, salt, and then water. And the water is actually in a baggie inside, a thin little bag. And the salt is inside the outer bag, and then there's a little bag with water inside of it. And you squeeze it, and the bag with the water in it pops, and it bleeds out into the salt, but it stays in the main bag. And you shake it up, and then that's a chemical reaction that occurs that is endothermic. It takes heat in. So when you pop the membrane, the two compounds mix, and a chemical reaction occurs that makes the pack feel cold. So En means In, like enter, right? So endo means in, therm means heat. So endothermic takes heat in. So an example would be a cold pack, an instant cold pack. Get that written down, pause. All right, an exothermic reaction is one that releases energy. It makes the substance feel warm as it is giving off heat into the environment around it. And again, I normally would bring one of these in, but I can't show you how hot it is to the camera. So again, if you aren't familiar with hot hands, maybe ask somebody if they take you to Walmart and buy you some. But the hot hands are used. Oh, sorry about that. Hot hands are used by hunters, people in band, people that are out hiking, camping. It's an air-activated hand warmer. And once you open a little plastic and it's exposed to air, the reaction begins. So it's got cellulose, which is just plant fibers, iron, so literally like little pieces of iron shavings, little black iron shavings, activated carbon, which just helps evenly distribute the heat, vermiculite, which is a type of thing that grabs onto water in the air, and a little bit of salt. And when you open it and expose it to the air, there's a chemical reaction that occurs when the moisture in the air reacts with the salt and the iron, and it begins to rust. So rusting is an exothermic reaction. If you were to go out to a place that was full of rusty vehicles and scan the temperature of one spot on the car and then scan the temperature of a spot where it was rusting, it would be warmer because rust is an exothermic reaction. So X, like exit, go out, therm meaning heat, so puts out heat. I got to let in my study hall, but I'll be back to finish. All right, so pause, get that stuff written down. Last thing is just review of what we've been talking about. So normally I would have you draw in these boxes. And I mean, if you want to draw on your notebook instead, these are for your notes. So, but I want you to give me at least one example of physical, one example of chemical, one example of endo, one example of exo. So a physical change, something that doesn't make a new substance. So cutting, folding, boiling, freezing are all physical changes. Chemical changes are going to be one where you get a new substance that has new properties. So baking, burning something, leaves changing color. Rust is a chemical change. Endothermic reaction is going to be a chemical reaction that takes heat in. Endothermic reaction is one that takes heat in. It's going to be a chemical reaction, but it's going to take heat in. Enter, endo. So something that feels cold. So our instant cold pack was our example of that. Now, not the kind that you have to put in the freezer and let it cool down. That's a physical change. This is the kind where you keep it in your first aid kit and you have to break it to get it to be cold. And then finally, exothermic reaction is going to, why does it do that? Like, seriously. I mean, it just went all the way back to the beginning. Exothermic reaction is one that puts heat out. Heat is released. So rusting was an example, but the hot hands uses rust to do that. Okay, wow, that was real painful, but we did it. Okay, bye.